Okay, so hopefully this time there are no glitches. Other glitches is Olga, my colleague, or Eyal were supposed to pass this presentation. I'm not the tungsten fabric expert in Mellanox. I'll do my best. The main focus of this presentation is not to teach you about Contrail, Open Contrail, or tungsten fabric as it's called today. The main focus is to try and present what is needed from the DPDK ecosystem and PMDs in order to enable tungsten or Contrail operation and offload. So there are many people here, OVS from Intel, from Mellanox, from Red Hat, probably others I didn't get to meet or discuss. I think we covered OVS during many discussions this time and over the past year or two. So this is a very brief tungsten and some more about what do we want from DPDK here. So Tungsten Fabric is SDN-enabled management control software, a centralized SDN, virtual router forwarder on a compute node, and it has both support for Userspace and kernel. It's one of the LFN projects now. And the vRouter part of the switch forwarding is actually similar to what OVS does, where it manages packet transfer, kernel or user implementation, and it's similar different in functionality and implementation in the details, but similar idea in high level. This originated more from the telco operators, and I guess that's part of where the difference or change or different implementation and functionality is coming from. So I'm not going to go into all the details, and we can spend, I guess, a full day learning about Tungsten and how it's built. I wanted to show the traffic pipeline, which is complicated. And again, I'm not going to go into the details, but it starts with a virtual interface that defines the virtual router function, and then multiple tables can be looked at depending on your tenant and the source of the traffic. L2 forwarding tables, and IP or L3 forwarding tables, next hop tables which define what to do with it, and at the end of the flow we have another virtual interface, and these virtual interfaces can be the wire port or the VMs, and it can go depending on where the traffic is coming from and going to. It can act as a router between multiple ports. It can act as a switch router between the VMs and different network layers. It can do different bridging or routing, support various tunnels. So again, coming from the telco, MPLS over GRE and MPLS over UDP is less standard, is not part of OVS, at least today. So it has some different protocols it's based on. A lot of securities and policies, mirroring, load balancing, a lot of telemetry. I'm sure OVS has. I'm not exactly familiar with the amount of details. I understood that the amount of telemetry and statistics analysis that can be taken out of Tungsten fabrics is more advanced or further down the road. So part of the challenge is how do we offload all these different functionalities. A lot of it, again, is going to be similar to what we've been discussing doing with the OVS offloads in partial or full offload. So part of the work we've started recently and working with the community is doing what we call partial offload. We can define RTE flows and set marks. So if we detect a specific tunnel or flow, we can detect this according to the destination IP of the vRouter. We can match according to tunnel classification, specific for, again, MPLS over GRE or over UDP, which are more specific for Tungsten deployments. MPLS label, or similarly to VXLAN and the VNI classifications. And then there's the specific tenant flow, the inner 5-tuple of the tunnel. So assuming hardware can specify or classify this flow, we can set a flow mark. And then when we receive the packet, the MBUF includes the flow mark, which allows the RX data path to bypass a lot of software classification and then save CPU and jump into the processing plane further down the road. So when an MBUF is received with a mark, not all of them have a mark, we can retrieve required forwarding information in a single lookup. Again, we touched this in the presentations of how do we do good hashes. So this saves the lookup and big hash in CPU. The hardware does this for you. We use the forwarding information to bypass all the classification lookup and then maintain other operations that exist in the regular software data path. So that's more a partial, what we call partial software, hardware acceleration. Hardware does some of the work. RSS, it should be very simple, but once you do RSS on MPLS over GRE, over UDP, we want to do RSS on the inner of these protocols. So it's a little bit more different than our common case of VXLAN or other more, I don't know if to say common tunneling protocols. But obviously, doing RSS in hardware with the right classification allows to bypass the redistribution or changing cores in software for the per packet. Okay, so part of what we want to do next, again in the vRouter, similar to what we are working on with OVS and the guys here, and we've discussed this, is allowing for full SRV support. Using the RT flow DPDK representers, which is work in progress in the DPDK in the last and previous releases of DPDK. We want to allow full data path, and I just put this again drawing so everybody remembers this complicated data path scenario. It means extending our RT flow to support rules, tables, groups, and actions which are partially there and partially not there and have to be added. And again, like a lot of the discussions and what I discussed earlier, improve the update rate in order to support hundreds and thousands and million rules in there. When I say SRV, it means that the application manages the data path and potentially some of the data will go directly to the application through the direct attached VF. So for this to work, we need to allow more complex multi-stage pipeline in RTE flow. That's work that's being worked on again in different areas. We want to allow a jump action between different tables, sometimes multiple jump actions in one go. We'll discuss this in a couple of slides. A steering registers is a new idea. Basically, in this flow, part of the information that's being taken here and here will be used for later lookup. So based on initial flow classification, we want to save some metadata with a packet and let the hardware use this in further lookup tables it's being processed. So steering registers, which can be as an input or modified or classified by during the pipeline, is something we'll want to add. And then a different kind of RT flow for hints for the table. We want to match on wider wildcards. I don't know, maybe it's a range of MAC addresses, and part of this is already available through the RT flow. It's not something new, but it's not necessarily implemented, at least by our PMD, and I don't know about the other PMDs around. An interesting question here is, longest prefix match. So we have a software implementation. I understood from Thomas that recently it was even updated or improved the IPv4 implementation of it. How do we do hardware hooks to allow LPM to be implemented in hardware? So packet on the egress flow will be able, or ingress flow will be able to go through the entire classification, routing classification and LPM in hardware and reach the correct decision and action moving forward. So maybe we should hook it into the libRT LPM. We haven't looked into that much further, but it's something we're starting to think and see, and I'll be happy to discuss if anybody has or was looking at this later on. More features which are needed by the vRouter, a mirroring packet. So a packet has arrived and it wants to mirror the packet to some logging instance or debugging. So you want to classify and then split the packet. One packet will go through the regular flow all the way to the queue to the application or to the VM, and another packet will go through a different set of actions encapsulated with some new destination, maybe inside the machine, maybe outside on the wire or on a different port. So do we add 2 jump actions? We have to try and figure out what's the right semantics to expose this. But mirroring packet is a feature used by vRouter and has to be done pretty soon. Load balancing, we have RSS on the input, so we know how to distribute to multiple queues. In this case, it's the other way around. We have a single send queue, and we want to distribute this into different destinations with different routing decisions in hardware. I don't know even to tell you if we can do this in Mellanox in the current hardware we have. But we want to be able to expose such a feature and make sure that it becomes a target for next generation, if not current generation. Obviously, FPGAs can probably implement this faster, or Softnik can implement this faster regarding the other. So again, some ideas of how to do this. Do we want to provide an array of actions? How do we specify this? How do we specify the hash, which will define the next lookup on the tables and be able to split this into multiple different actions on the way out? And of course, like any other virtual router, forwarder application, high rate of rules in action, statistics. Here it's very, very critical. Statistics is, again, very basic part of the contrail. Multi-millions of rules and actions and counters. We want to be able to configure them very fast. We want to be able to read them very fast. A lot of the challenges are going to be around the scale of RT flow for the next year or two. So that's it on cue. A very short introduction or what's needed that I think part of it was not discussed until now at least.
Any questions? We have 2.
There's one here in front.
Can you hear me? Yes. The extensions to the RT Flow API that you have suggested here basically sound like we are doing another OpenFlow, right? It's exactly the same constructs that have been added to OpenFlow 1.0 over time. How do you see this?
So there are different kind of applications. We have a OVS and with OpenFlow, and we have Tungsten, and we have a VPP which is in there as well. And in my previous presentation, I said that a lot of other vendors have their own proprietary closed source solution, which they don't talk about. So they're all competing in the same space. Some of them are targeting different business justifications or customer use cases, sometimes more security, sometimes faster time to market. So it depends on the market. What I was trying to expose here is these different applications want different services. In DPDK, I think we should try and expose a single interface or single abstraction to allow these different implementations to work on top of DPDK. I'm not trying to challenge one compared to the other, which is better, which is not. I'm guessing they're doing it between themselves good enough.
Yeah, that was not what I meant. I was really talking about this low layer interface to offload the stuff to the hardware. That is becoming another open flow protocol, shared by all sorts of different vSwitches, OVS, VPP.
So you mean the RT Flow API itself?
Yes, the RT Flow API.
I'm not sure if I know how to answer this. I mean, DPDK in the past had a few flow APIs which were more specific to vendors, and I think RT Flow today was designed and is much more generic. It doesn't fit one hardware specifically. It's more of a generic API that can be extended, and different vendors can implement their support for it underneath.
So I guess.
Thank you.
Just time for 2 questions, but if you can carry on, maybe in the breakout after.
Okay.
I think we had just one.
Yeah, just wondering, does the vRouter data plane do IP reassembly?
Excuse me?
Does it do IP reassembly?
I don't know, but obviously, if you do full hardware, then something has to support this. In most of these solutions, if we're looking at OVS or vRouter, Contrail, VPP, so in most of these cases, if hardware cannot support this, there is a fallback to the software path. That's one of the reasons. I mean, if it's full hardware offload, so you can ask why do this in DPDK at all? Okay, you can do this in kernel and just offload everything to the hardware anyway. You don't have data path. So IP fragmentation, sometimes IPsec, all sorts of new protocols which are used, or different layers, are not always implemented in hardware. And then you have to have, for part of this at least, the software fallback. And DPDK is a much faster software fallback than hardware. So if there's IP fragmentation, at least these packets might go to the software queues and go through a slower path. It's still faster than kernel, but...
Okay, but you didn't have any ideas around hardware offload for IP reassembly?
No, I'm not familiar at least. I know that we have some ideas in Mellanox on how to implement some hardware support for IP fragmentation, stuff like that, but nothing concrete.
That's correct. Thank you,
Okay.
Alex.